Conceptual Introduction to Linear Regression, Part 5, Practice with Linear Transformations. I'm going to go over a bunch of simple transformations to the variables. In the hypothetical experiment that we've been talking about, each minute of practice was associated with about 0.11 extra math test points. So, before I do any transformations, think about how many extra points would we expect from 10 minutes of practice. If 1 minute of practice confers 0.11 math test points, then 10 minutes of practice should confer 1.1 math test points. Remember, this model is a straight line, so everything multiplies out nicely. So what if I make a new variable by dividing the practice time by 10? The new variable will have units that are 10-minute increments. If I used that variable instead, what would the slope be? To answer that question, think about what the slope would mean. The slope is the expected differential in the response variable for a 1-unit differential in the predictor. And a 1-unit differential on that new predictor would represent 10 minutes. We already said that 10 minutes of practice confers 1.1 math test points. We can see that based on our existing output. So dividing practice time by 10 should result in a slope of 1.1, 10 times higher than this slope we see. Let's try it. Here's a histogram of the original practice variable. The units are minutes, and it ranges from 0 to 120. The 1 hour mark is right in the middle, 60 minutes. And here's a histogram of practice divided by 10. I hope it's clear that it's fundamentally the same variable, just with different units on the x-axis. An hour, the middle of the distribution, is 6 10-minute increments instead of 60 1-minute increments. Here's the result of the regression model with the predictor divided by 10. The slope is 1.1, just as we expected. A 10-minute increment in practice was associated with a 1.1 unit increment on the math test. The standard error is in the same units as the slope, so it got multiplied accordingly, but everything else is the same. Dividing the predictor by 10 left everything about the regression model the same, except the slope and its standard error, because it changed nothing except the units of the predictor. What if I divide practice time by 60 instead of 10, so that its units will be hours instead of minutes? Here's a histogram of the original practice variable again. You can see the 1 hour mark there in the middle, 60 minutes. And here's that same variable divided by 60. Now the units are hours instead of minutes, but again, it's exactly the same variable. The 1 hour mark in the middle is labeled 1.0 instead of 60. Fitting the regression model with the practice divided by 60 variable results in a slope that's 60 times higher than the original slope, but otherwise the model is unchanged. Now the practice variable is measured in hours, so it should make sense for the slope to be 60 times larger. It is the expected math test benefit from practicing an additional hour, rather than from practicing just an additional minute. It's saying the same thing in different units. The slope indicates that participants got about 6.8 extra math test points for each hour of practice. Okay, so currently, 0 practice is 0 units on our predictor variable. But what if 1 hour of practice, for some reason, was some kind of standard, a baseline against which I wanted to compare everyone? What if I wanted to treat 1 hour of practice as the reference point and consider how many minutes more or less than that hour people practiced? Here, I've again computed a new variable based on the original practice variable. This practice over 1 hour variable is practice in minutes minus 60, then divided by 60. This variable will be 0 at 60 minutes, 1 hour, and its units are hours. 1 unit is 1 hour. So the value will be -1 for people who practiced an hour less than the 60-minute reference point. In other words, people who didn't practice get a score of -1 on this measure. And this variable will be +1 for people who practiced an hour more than the 60-minute reference point. Here's that histogram again. All we've done is shifted the units so that now 0 represents 1 hour of practice, and the other numbers count how much more or less than that someone practiced. We just got through looking at a regression model where the units were 1 hour. With this new variable, will the slope be the same or different? It will be the same, because we haven't changed the units of the variable. We haven't multiplied or divided it by anything. 1 unit is still 1 hour. What about the intercept? Will that be the same or different? The intercept will go up it will go up by 6.8. That's how much higher test scores were for people who practiced an hour compared to people who didn't practice. The old intercept was people who didn't practice, and the new intercept will reflect people who practiced an hour. So here is the regression model output with that transformed version of the variable. Sure enough, the slope is still 6.8. The intercept is now 55.8 instead of 49.0. It went up by 6.8 because it now represents people who practiced an hour instead of people who practiced no hours. Everything else about the model is the same. A quick detour. Let's talk about standardizing a variable. The standardized version of a variable is what you get when you subtract the mean and then divide by the standard deviation. This process is also called z-scoring. It quantifies how many standard deviations from the mean each value in the variable is. Using this variable in a statistical model will change the units to standard deviations instead of the original units of the variable. It will also change the reference point to the mean of the distribution. So now I've z-scored, or standardized, the practice variable by subtracting its mean and then dividing by its standard deviation. Instead of minutes, the units are now standard deviations of practice. Each standard deviation of additional practice time was associated with about 4 more points on the math test. This is just like the other linear transformations that we did. It involved subtracting and dividing, just subtracting and dividing. So the straight line is conceptually the same straight line, but the units are different. Here I have z-scored or standardized both variables, practice time and the math test score. The slope comes out to 0.39. One standard deviation of practice was associated with 0.39 standard deviations of math test scores. Note that R uses scientific notation for the whole column when any values in that column get too big or too small. So the intercept is essentially 0 here, and that's why the column is written in scientific notation. 3.9 times 10 to the negative first is 0.39, so the slope is 0.39. Note that the t-test of the slope has stayed the same throughout all of the linear transformations that we've looked at, because it represents the same straight line going through the same set of points, the same variance explained, just different units. So with both variables z-scored, the slope comes out to 0.39. R also has a function called core.test. I used it here to get the Pearson correlation coefficient. That's the regular kind of correlation coefficient, the one that we normally just call correlation. The core.test function also gives the usual t-test comparing the correlation to 0, the normal kind of test we do to see whether a correlation is statistically significant. On the previous slide, we saw that z-scoring or standardizing both variables gave a regression slope of 0.39, and here we see that the correlation is 0.39. The t-test details and the p-value are also identical. The correlation is just the slope between z-scored or standardized variables. I'm going to say that again. The regular old correlation coefficient is the slope between standardized versions of both variables. So for a correlation of 0.39, we could say one standard deviation of additional practice time was associated with scores on the math test that were 0.39 standard deviations higher. That's a reasonable interpretation for any standard Pearson correlation, because correlation is standardized slope. It might be hard to imagine why z-scoring both variables makes it so that the slope does not even depend on which one is the response and which one is the predictor, or the units of either variable, and it becomes this unitless standardized statistic. I have a page on my website that tries to make this idea more visually intuitive. See the URL on the screen if you're interested.